Hello and welcome to lectures on state space approach to control system analysis and design. So far we have studied the first principle based mathematical modeling of systems, thereafter solving the state equations, stability, controllability and observability, and methods of control system design. Now we are at a proper footing to take up case studies. Now if you look at popular textbooks, then the case studies are of variety of types. Some author has considered antenna control, some author has considered inverted pendulum, some author chemical plant, etc. However, in this case, in my lectures, I take example of nuclear reactors. And in a few videos today and in the subsequent, we will see the mathematical modeling, linearization, control design pertaining to nuclear reactors as a case study. So let us begin with that background. Of course, there is an apprehension in public mind about nuclear reactors. However, let me assure you that system designer and other concerned project people that nuclear reactors operate with utmost safety. And as far as the control engineers are concerned, the fraternity to which we belong, absolutely the nuclear reactor will look like any other system. As you see the various deliberations in this lecture, this point will be further reinforced into your mind. So let us begin with that. This I will have a few minutes of introduction, and there might be some overlap with one of the lectures which we took in the first week. So a nuclear reactor is a device in which a controlled type of fission chain reactions take place. Now there are usually two types of energy producing nuclear reactions. One is fission and other is fusion. And most of the nuclear reactors today are operational. They are fission reactors. And in the nuclear reactor, the fission reaction chain is established and thereafter maintained so as to produce constant flux. This is what happens. There are so many such interactions, nuclear reactions are taking place simultaneously. We consider one of them. A neutron at an appropriate energy bombards on nucleus of uranium-235 and it gets absorbed into that. The compound nucleus, which now contains an excess of neutron, is in excited state. It has very high internal energy and thereby it breaks into pieces, breaks into two fragments, so-called fission fragments, and simultaneously it releases about 200 million electron volts of energy and more than two neutrons, sometimes 2 neutrons, sometimes 3 neutrons. These neutrons, they may get further absorbed, leak out, or they may cause further fission. And if the number of neutrons which were utilized in one generation is equal to number of neutrons that emerge from fissions, if there is a balance, then the neutron flux in the nuclear reactor will remain constant. And that is the ultimate aim of operation and control of a nuclear reactor. That is what we mean by sustaining or maintaining chain reaction in a nuclear reactor. This is a schematic of a nuclear power plant. Basically, a nuclear power plant is the one which produces power based upon nuclear energy, based upon the fission energy generated in the core of the nuclear reactor. So this shows the reactor. We will see in the next few slides the various components of the reactor, but they are also shown here. The core consists of fuel, moderator, and the coolant. Coolant circulates, moderator also circulates. There are control rods. Their function is to control the speed of the chain reaction. And the neutron flux is sensed by some kind of detectors, which are usually fission chambers. And after amplification, it is sent to control room for the purpose of monitoring and control. It is utilized through a control system. It drives the control rods. The heat produced in the core, that 200 millions of electron volts, which is generated in each of the fission, and there are 10 to the power 9 or even higher number of fissions are taking place per second in the reactor. That much energy is conveyed by an appropriate coolant, which is pumped through the core. It comes out in a steam generator. It passes the heat to secondary side. There the water gets converted to steam and it drives the turbine. Turbine is coupled to the electrical generator and it produces electricity which is fed to the grid. This is the usual schematic of a nuclear power plant. Now sometimes this coolant directly comes into boiling state and it can drive the turbine. So this intermediate, this heat exchanger, the steam generator, is there in some designs. It is not there in some other types of nuclear reactors. But the idea is to heat the coolant in the core and then to drive the turbine to produce electricity. So as we see the scenario in the world, the first commercial nuclear power station started in 1950s. Today, the nuclear energy provides about 10% of the world's electricity from about 440 power reactors. And 60 more nuclear reactors are under various stages of construction and commissioning in the world. Recently, there is a drive to minimize the carbon released to environment, and nuclear reactors are getting further boost. You might be aware of this. Besides all this, over 50 countries utilize about 220 research reactors. And of course, besides research, the reactors are utilized to produce medical and industrial isotopes. This is another very important utilization of nuclear reactors in various types of these treatments. You might be aware, like PET, nuclear, it is the isotopes which are used, and these isotopes are produced in nuclear reactors or accelerators. Similarly, the isotopes produced in nuclear reactors, many of them they are gamma emitters, and this gamma is used for irradiation of food, and it has several applications in the area of food preservation and agriculture. So there are industrial applications also, so many are there. So nuclear reactors, of course, majority of them are used for power production and research, but even a huge number are used for medical and industrial isotope production. As regards the scenario in our country, India, the first commercial nuclear power station was built in 1968. Research reactor came at Trombay even earlier. You might have heard about the Cyrus reactor. It came even earlier, and in fact, Apsara came earlier to Cyrus, which was established at Trombay. But as regards the commercial power production, a commercial nuclear power station came at Tarapur in Maharashtra, India in 1968. By the end of the last year, 2023, 23 power reactors are operational in the country, producing approximately 7.5 gigawatt electrical energy. There are 4 research reactors, 2 at Bhabha Atomic Research Center, Trombay, and 2 at Indira Gandhi Center for Atomic Research at Kalpakkam in Madras. These 2 reactors at Bhabha Atomic Research Center are the Dhruva reactor, which is a 100 megawatt thermal reactor. It doesn't produce electricity, it only produces isotopes and is used for neutron beam research. There is the newer one is called as Apsara upgraded, and this reactor is again used for neutron beam research and some irradiation purposes. 2 research reactors at Indira Gandhi Center for Atomic Research. One is called as the Fast Breeder Test Reactor. Or the FBTR, and other is called as Kamini. So Kamini is a very small reactor rated maximum of 30 kilowatts. Fast breeder test reactor is rated 20 megawatt. Both these reactors are operational at Kalpakkam. And at Trombay, as I told, one is Dhruva and one is Apsara U. Let us proceed. Reactors are classified as fast reactors and thermal reactors based upon the energy of the neutron, which actually initiates and sustains the fission chain reaction. So in fast reactor designs, the neutron energies are above 10 kilo electron volts, greater than 10 keV, sometimes in million electron volts range. These neutrons cause fission, and in thermal reactors, the low energy neutrons or the thermal neutrons, they cause fission. Their energy is less than 1 keV. In fact, many of them are in 100 eV range, which cause fission in thermal reactors. And thermal neutron is a neutron which has energy at equilibrium with the energy at the room temperature of around 25-30 degrees C, so which is of the order of 0.025 eV. Of course, the energy of neutron in thermal reactors is little higher, and it will be, of course, up to from a fraction of electron volts to less than a keV. That is the range of thermal energy, and that is the energy of neutrons which cause fission in thermal reactors. So in the previous slide, where I showed the schematic of fission, these neutrons which come out from the fission, they have high energy. And in a thermal reactor, their energy is so high that they will not be so effective in causing the fission reactions. So they are slowed down, their energy is brought down, and then they are utilized in thermal reactors for sustenance of the chain reaction. In India, there is only one operating fast reactor, which is fast breeder test reactor at Indira Gandhi Center for Atomic Research, as I told just a while ago. Of course, a prototype fast breeder reactor PFBR 500 megawatt is under commissioning at Kalpakkam, same place, a few kilometers away from the fast breeder test reactor, and in the vicinity of the Madras Atomic Power Station, which is a PHWR unit. So these are the only two fast reactors in our country, in India. Remaining all reactors are thermal reactors. We keep in mind this. Then nuclear reactors are also classified based upon the type of coolant which is used. And majority of reactors in the world use the light water coolant. Light water means H2O. This is the common water which we use for a variety of other purposes. So demineralized light water, this is only to distinguish from a word heavy water. I will explain. So this light water, here it is compound of hydrogen and oxygen, and hydrogen, as we know, it is 1H1. So the water containing hydrogen and oxygen as its constituents is the coolant in light water cooled reactors. So nuclear reactors are also classified based upon the type of coolant they use. And majority of the reactors in the world use the coolant which is normal water, and in the nuclear parlance it is called as light water to distinguish it from heavy water. So light water means the compound of hydrogen and oxygen, and we know hydrogen is 1H1, one proton and one electron. There is no neutron in the nucleus of this hydrogen. And light water reactors are further of two types. One is boiling water reactor. The water boils inside the reactor core, and that steam water mixture enters after separation to turbine. Steam enters and the water is recycled back. So in the boiling water reactor, steam is formed inside the reactor. PWR or pressurized water reactor again uses the same coolant, light water coolant. However, it is pressurized not to allow boiling inside the core. And this design is better, the characteristics are improved, and then subsequently the heat is passed from this reactor coolant through a steam generator to the secondary coolant, and that secondary coolant drives the turbine. There are heavy water cooled reactors. In our country they are in majority, and they are of pressurized heavy water reactor type. The heavy water coolant generally we denote is by D2O, but this D is again a hydrogen isotope which has also a neutron in its nucleus. So it is 1H2, and so it is heavier than hydrogen, and so we call it its compound heavy water, just to distinguish from light water. So these terminologies are used in nuclear area, light water and heavy water, and we understand that both are water. However, one is containing deuterium, which is the denoted by D, but it is 1H2 chemically. So we have pressurized heavy water reactors in India, and ASWR is at design stage. It may come sometime in future. Then many reactors are operated in which the cooling medium is gas, helium for example. They are there, and there are reactors cooled by liquid metal, for example sodium or sodium potassium, or there are some eutectic lead bismuth, etc. The important main components of a nuclear reactor are the core, and the core in turn consists of, this is where we find fuel, the moderator, the coolant, and the control rods or control elements. Fuel, as we know, is the one where fission interaction goes on, happens, and energy is produced. Moderator, its function is to bring the fast neutrons which are produced in the fission to thermal energy. They slow down the neutrons and they are called moderators. Coolant is the one which conveys the heat from the core to outside the core to a separate medium, or where it gets converted to steam and drives the turbine. And control rods or the control elements are those components which are used to control the rate of fission chain reaction. For a control engineer, they are the most important components in a nuclear reactor. Besides these, there is reflector. The core is surrounded by reflector. This outer one will be reflector, and it is further surrounded by shield. The reflector's job is to send back neutrons which would have otherwise leaked out. From the core, neutrons try to go out and reflector sends them back. And shield's job is to not to allow the nuclear radiation, neutrons and alpha, beta, gamma, mostly gamma, because alpha, beta, they are quickly stopped, but gamma, that has larger penetration power, and a shield is used essentially to stop all these three forms of radiation. So outside the reactor boundary, the radiation levels are very small. Then outside the containment, this whole thing is inside a containment. You might be aware of this kind of thing. Outside the containment, there is almost nil radiation, or there is only background radiation. So besides all this, again important for a control engineer is the instrumentation. And if I go back, there are two types of neutron flux measurements. One is this one. So a detector is located just outside the core and it measures the neutron flux in the core, the average neutron flux. It is called as the X-core detector. However, detector can also be placed inside the core, and that is called as an in-core detector. So these two are flux measurements carried out in operational power reactors. Besides that, thermal power is measured. This one. The reactor thermal power is measured in some manner by measuring the steam flow and enthalpy or temperatures, etc. And electrical power is another quantity which is available for measurement. So many such instrumentation are useful for reactor operation. They are there. So of course, for this lecture, because this is only a case study and I am trying to present a simpler picture, we will consider one neutron flux sensor either in core or X-core, but it gives reading, it gives a measurement signal proportional to the neutron flux density in the reactor. We will come to that again. That is the only instrumentation we are considering. Now, with that background, we come to mathematical modeling of nuclear reactor. And there will be a little overlap. This is enhancement over what was done in one lecture in the first week, where we considered the modeling of a nuclear reactor as an example. So we first consider the mathematical modeling of core, and essentially the fission reaction which takes place in the core. So the neutrons which are produced in fission, they fall into two categories. One is called as the prompt neutrons. These are the neutrons released almost instantaneously with the fission, or within a very short time of the order of 10 to the power minus 14 seconds. There are other category of neutrons, they are called as delayed neutrons, and they are produced due to radioactive decay of some of the fission fragments. So as I showed in the previous slide, a few slides previous to that, the compound nucleus breaks into fission fragments, and when it breaks up, it also releases 2 to 3 neutrons. Now majority of them are prompt neutrons, but those fission fragments which are formed, they undergo radioactive decay, many of them, and when they decay they release neutron, and that neutron is called as delayed neutron, and their production will happen sometime after the fission event and sometime after the production of prompt neutrons, and that time depends upon the decay half-life of the precursor. That fission fragments which produces delayed neutrons is called as the delayed neutron precursor. So depending upon the half-life of the delayed neutron precursor, the neutron will be released, the delayed neutron will be produced a few milliseconds to up to 3 seconds later than the production of prompt neutrons. This happens usually in 6 groups. So there are 6 identified delayed neutron precursors. Some of them have decay half-life of the order of few milliseconds, few tens of milliseconds, and some have half-life up to of a minute or so. So these a realistic modeling, a detailed modeling should consider all the 6 groups of these delayed neutron precursors, but we will consider the one so-called single group approximation, in which we will consider only one group which is a representative of all the 6 groups, and a decay half-life which is derived from the decay half-life of all the entire spread is lumped into one. So one decay half-life. Now this is what I told, that we lump all the delayed neutron groups into one effective group. Beta is its fraction and lambda is its decay constant. Decay half-life will be depending on lambda inverse. So if nu is the total number of neutrons coming out in each fission, that 2 to 3 neutrons, that is nu, then nu times 1 minus beta is the prompt neutron per fission, because beta is the delayed neutron fraction. So 1 minus beta is the prompt neutrons fraction, and fraction multiplying the total number is nu 1 minus beta, and that becomes the prompt neutrons released per fission. And so nu beta will be the delayed neutrons released per fission. But these come immediately, they will come later, depending upon that half-life or the decay constant. So if we consider a unit volume of the reactor, in one unit volume of the reactor, this neutron absorption is going on, and its rate is given by neutron absorption cross section into the neutron flux. Neutron flux is neutron density multiplied by neutron velocity. Neutron density we denote by eta in this lecture. The neutron density is number of neutrons per unit volume per centimeter cube, and v is the velocity of neutrons, and we consider that all neutrons have the same speed. So n times v, eta times v gives the number of neutrons which will actually impinge upon, fall upon any target, any nuclei. And so sigma a times lv, sigma a which is called as macroscopic cross section, it is a kind of proportionality constant, because not all the neutrons which impinge upon a target material will actually undergo absorption. Many of them will escape absorption. So only that sigma a times phi are getting absorbed, and so interaction rate is sigma a times phi. For absorption, fission interaction is taking place, and its rate is in a similar manner sigma f times phi. There A was for absorption, F is for fission here in a similar manner. So sigma F phi is the number of fission interactions which are taking place in the unit volume of the reactor, and in the complete core volume it has to be multiplied by the volume of the core in order to get all the interactions going on. Now if this is the number of fission interactions, and we saw that nu times 1 minus beta is the number of prompt neutrons from one fission. So fission rate into the fraction of prompt neutrons released in each fission, that gives the rate of production of prompt neutrons. So it is this. Delayed neutrons, as I said, will come through decay of delayed neutron precursors, and that takes time. So of course the delayed neutron precursors are produced in that fission immediately, and that will be nu beta times rate of fission. Rate of fission is sigma f times phi, and nu beta times sigma f phi is the rate of production of delayed neutron precursors. Rate of production of delayed neutrons, this is the radioactive decay rate of delayed neutron precursor, which is decay constant into the concentration of the delayed neutron precursor per unit volume. So lambda times psi is the rate of production of delayed neutron. This I have already said. The phi is a product of neutron density and volume. Neutron density is number of neutrons per unit volume per centimeter cube, and v is the velocity of the neutrons. We assume uniform velocity. Now if we see the neutron balance, the neutron density in the core changes like this. This is the rate of production of prompt neutrons. They come immediately, and this is the rate of production of delayed neutrons. So at any time, two streams of neutrons are there. One is prompt neutrons, other is delayed neutrons. So this is number of prompt neutrons, this is the number of delayed neutrons. So this is the total production rate, this plus this. And these many neutrons are being lost. Neutrons are getting absorbed. Of course, neutrons are also lost by leakage. At the moment, we are not considering that, to keep the treatment simple, mathematical treatment simpler and just simple, so that we can digest it, a control system engineer can understand it. The experts will build up more complicated models, but the final form is identical. So this is the prompt neutrons, this is the delayed neutrons. Their sum is the total number of neutrons per unit volume being produced per second, and this is the number of neutrons being lost through absorption. So this is the production rate, this is the loss rate, and so the net rate of change is d eta by dt given by the difference of production rate, which is these two terms, minus the loss rate. And this term is expressed, phi is substituted as V, NV, eta into V, eta, and that V is substituted, that basically V into sigma A, that has been taken common and some manipulations have been carried out. So what has been done, this has been divided by sigma A, phi has been substituted by eta times V, and that sigma A, because we divided, so we are also multiplying, and just a rearrangement. So it is written like this: nu sigma f by sigma A 1 minus beta minus 1, and this we are denoting by K. It is slightly different from what is called as effective multiplication factor. We have done some other approximations, as we are not considering leakage. This is not truly the effective multiplication factor, but even if we consider the leakage, the K comes here, and then it is the effective multiplication factor. So this is not the exact expression for K, but for our purpose we take it as expression for K. And similarly, this is not the exact expression for L, which is called as the prompt neutron lifetime. It is slightly different than this, but we take these two expressions as valid expressions for our purpose. In fact, we will not use these expressions. We assume that K is known and L is known. So it comes into this form, and slight more manipulation. This we divide by K, and so this K minus 1 divided by K and minus beta K, that gets rearranged like this, and we get K minus 1 by K minus beta divided by L by K. L by K is now called as prompt neutron generation time. L is prompt neutron lifetime here, and this K minus 1 by K, which is called reactivity. So we introduce this notation and this notation. So this expression further simplifies to this expression. Let me keep it clean. So this expression becomes this expression, and here rho is called the reactivity, as I said. Essentially, this is the input to the reactor, and its variation leads to variation in neutron density. We'll see. Now coming to the delayed neutron precursors, as I said, their formation rate is nu total number of neutrons into that fraction of delayed neutrons. Nu beta is their formation rate from each fission, and number of fissions taking place per unit volume is sigma f times phi. So nu beta into number of fission interactions, that gives the total number of delayed neutron precursors formed in one unit volume of the core. And delayed neutron precursors are decaying. Decay rate is proportional to their population, because this is radioactive decay rate, so it is proportional to population, and that constant of proportionality is lambda, the decay constant. So at any time, the rate of change of delayed neutron precursors concentration is given by this expression, and which becomes this. What we have done, nu sigma f we have divided by sigma a, and to balance we have also multiplied by sigma a. So nu sigma f by sigma a, and then phi t is expressed as V into neutron density. Phi is eta into V, neutron density into the velocity. So that substitution has been done, and so this comes into this form. And this we had defined as K, and this we had defined as 1 by L star. K was defined as nu sigma F by sigma A, and L star was defined as 1 by V sigma A. So we make these substitutions and we get this expression for time variation of delayed neutron concentrations. So we got one equation for neutron, this one, neutron density, and this is the second equation for the delayed neutron precursors. So with that we get the model of the core, this one, and this is called as the point kinetics model of the reactor. So essentially in the core, because core is a few meters in diameter and height or length, cylindrical core, and every location may have different interaction rates for the same phenomena, fission and absorption. They go throughout, happen everywhere in the core, but there may be minor differences here and there. And the average characteristics is represented by this point kinetics model. Just now what we derived is known by point kinetics model. So it is this. Now most reactors use uranium-235 fuel, and for them beta is 0.0065, it is a fraction, lambda is 0.08 inverse second, and L star is 10 to the power minus 5, a typical value, but it may be up to 10 to the power minus 3 second. Beta also in some reactors is slightly higher even for uranium-235 fuel depending upon the energy. So for example, PSWRs, they utilize beta equal to 0.0075, maybe around that. And for other reactors where either uranium-233 or plutonium is the fuel, beta is smaller, which is of the order of 0.003. But we are going to consider a uranium fueled reactor, uranium-235 fueled reactor, and so for that beta is this much, lambda is this much, L star we will take for this much. Now, as I said, for a control engineer, the measurement of neutron flux is important and there should be a way of controlling. So we will also model the instrumentation for the neutron flux density. So if I show this as the core, this is the, let us say, the cylindrical core, then somewhere near it, just at the boundary of the core, there is so-called ion chamber. And this ion chamber gives current proportional to the incident neutrons in its chamber. These neutrons interact inside the chamber. The material selected in the chamber is such that the neutrons cause current through either emission of alpha or beta or neutron further. And that current is converted to voltage and amplified. So at the end we get a voltage signal or a current signal. We consider in this lecture that signal as voltage signal, which is proportional to neutron density. However, the amplifier will have a little time constant, a few milliseconds time constant, and its transfer function is given by this, that the voltage divided by the neutron density in the core, the Laplace transform, is k by 1 plus s tau. K is usually 10 volts and tau is of the order of 100 milliseconds, 0.1. It is in milliseconds only. That is the measurement of neutron flux density. And if we convert this into state space form. One of the lectures was how to obtain state space representation from transfer functions. This one is very simple. We just cross multiply the terms and rearrange and take inverse Laplace transform. So we get this one. Time rate of change of this output voltage of the amplifier equal to -1 by its time constant into the value voltage and k by tau neutron density eta. It comes into this form. Neutron flux, that this detector current after amplification, after conversion to current and voltage, then amplification, we got n, that Vn. Now it is also differentiated. So there is a differentiator d by dt circuit and it produces dVn by dt. The output voltage of differentiator, which is denoted Vr, is proportional to dVn by dt, and because Vn itself is proportional to neutron density eta, so it is proportional to this Vr is proportional to d eta by dt. So in nuclear reactors, in fact, nuclear reactor instrumentation is much more complex. I am giving a oversimplified picture. In the low power range, it has different set of instruments. In the intermediate power range, it has another instrumentation and amplifiers, and then in the power range. So in the low power range, the flux measurement is logarithmic and rate is logarithmic rate. What I am discussing is the power range, in which both are linear. That output of the amplifier is linearly proportional to the neutron flux density, and similarly this rate is proportional to the rate of change of neutron flux density, this Vr. So there are only two instruments for the purpose of discussion of nuclear reactor in the power range, which we are going to do in this lecture. The typical transfer function of this differentiator is this one. Neutron density is the input, voltage proportional to neutron density is the input, and the rate signal is the output. Vr by Vn, Laplace transform, is given by this first order model, where Kr is typically 100 and this tau is of the order of 2 seconds. This time constant is large compared to the time constant of that other amplifier, in order to suppress the noise which gets otherwise amplified because of the differentiation. In fact, in the low power range, this time constant is much larger. It is of the order of 6 to 15 seconds. And in fact, at very low power, it can be up to a minute also. So here in the power range, it is small, but is still of the order of 2 seconds. It needs to be considered. Now again, this transfer function can be converted into the state space representation. So what we do is, let me just indicate here that Vr by Vn, it is Kr S by 1 plus S tau R. Now we cross multiply, so Vrs plus S tau R Vrs will be equal to Kr S Vns. We bring these two terms together on one side and this on the other side. So what we will have, S tau R Vr minus Kr Vn equal to minus Vrs. and we can divide it by tau r. It becomes this. And what we do is we want to identify this as state variables. So we rewrite that other side as Vr minus Kr by tau r into Vns Vrs. We force write this term, and that means that we have to, because this is minus sign, so it is added, so we subtract. So we subtract Kr by tau r square Vns to keep it balanced. And we identify this term as state, so Vr bar is identified as Vr minus Kr tau r into Vn. So this becomes S Vr bar S equal to minus 1 by tau r Vr bar S minus Kr by tau r square Vns. And then we take inverse Laplace transform. So this one will give dVr bar by dt equal to minus 1 by tau r Vr bar minus Kr by tau r square Vn. And this is the relationship here, and this relationship was the other relationship. So utilizing the well-known methods of converting a transfer function to a state equation, this has been converted to this state equation and this form. So thereby we got a state equation characterizing the dN by dt. Now we need to model the reactivity variations. The variation in reactivity rho, they are affected through a control rod. Now if you see the expression for rho, it is k minus 1 by k. Please recall, it was there in the lecture a little while back. And k in that is nu sigma f by sigma a. So it depends on sigma a. So if we push a rod containing excess of neutron absorbing material inside the core, then it will cause reduction of reactivity, and it will cause the reaction rate to slow down, to happen at a slower rate. And if we pull out that same rod, removing the material containing absorber, then the reaction rate will become faster. And so a control rod is used to change this sigma a and thereby the reactivity rho. When it is at equilibrium, the reaction rate is constant. The design is such that the control rod at 50%, which in our case we are calling at the reference position of criticality, at that time the control rod is at zero position or at equilibrium position. When it is pulled out with reference to that, absorber reduces and the neutron fission interaction rate becomes faster. When it is pushed in reference to that position, the fission reaction reduces. Number of fission reactions per second reduces. And so thereby the reactivity is controlled. Now this control rod, as I said, its position is measured with respect to the equilibrium position, and so reactivity is directly proportional to the position, that control rod position, which is denoted by H. And this is the typical value for this K rho. Now this control rod is usually driven by a motor. It has its own time constant. However, we are ignoring the time constant of the motor, and so the speed of the control rod is directly proportional to the applied control voltage to the drive. dH by dt is Km times Vt, and Km is usually of the order of 0.004. So through that we account for reactivity variations. So this is essentially the control rod speed, and its integration is the control rod position, and that multiplied with k rho will give the reactivity at any time. So we can make use of this expression. And of course, all these voltages, this is the input voltage to control rod. Similarly, the output of the linear amplifier and that rate amplifier or differentiator, they are generally in the range of, for this one plus minus 10 volt, for rate plus minus 10 volt, but for linear amplifier 0 to 10 volt. There are some other phenomena. One is called as internal reactivity feedbacks. When a nuclear reactor operates on power, the temperature of various core components, fuel, coolant, moderator, and even the structural material inside the core, the temperature rises well above the room temperature. And thereby, because of change in temperature, the absorption characteristics differ, and that generates internal feedback. Similarly, many of the fission fragments, they are neutron absorbers. Not all, some produce like we saw, some will not absorb, but some will absorb, and they again introduce some kind of internal reactivity feedback. Then as the reactor is operating, the fuel will burn and number of fuel nuclei per centimeter cube will reduce with time. Even though it is slow, and even though refueling is done to bring back the fuel loading to equilibrium, nevertheless there is always a burn up of fuel and an internal reactivity feedback because of that. All these phenomena are there, but we are not considering. They introduce reactivity variations, but we are ignoring these phenomena. Then there are plant systems. As you saw that picture schematic in the one of the previous slides, then there are other components. As the coolant goes out, it passes heat to the secondary coolant. Secondary coolant drives a turbine. Turbine drives a generator. Now all these components have dynamics, and for a very accurate modeling that needs to be considered, but again, to keep the things simple, we are not considering this. Even in the actual work on nuclear reactors, a control engineer doesn't do modeling of those plant systems. It is assumed that the interaction between plant systems and reactor core is such that the impact of dynamics of plant systems on the core side will be small, and similarly the impact of core side dynamics on plant systems will be small. So they are treated in decoupled fashion, and we do the same. We do not consider the plant systems. Now with all this is the model equations we have at our hand. This is the rate of change of neutron density, rate of change of delayed neutron precursor concentration, rate of change of that linear voltage, rate of change of that differentiator output, and the rate of change of control rod position. These are the 5 equations we have. They are the differential equations. Additionally, we have 2 algebraic equations. One is this one, relating reactivity to the control rod position, and other relating the output of the differentiator to one intermediate variable VR bar and that voltage of the linear amplifier. And we have these various parameters. These are the neutronic parameters. This is the prompt neutron generation time, as we saw, and these are the other constants. They were quoted while discussing the equations. Now there are 5 differential equations, so the model order is 5. that we'll see. And then it has one input, that reactivity is input, and of course we will substitute this one there. So H is the input, the control rod position, and there are two outputs, that one Vn and that other one Vr. These are the two outputs. Then other thing we notice, I just go back to that equations. Here, this is K rho into H. If you open this, you will get a term K rho H T into eta T. Now both of them are states. H and T, eta, both are states. So this term is containing a product of two states, and thereby it will behave in a nonlinear fashion. So nuclear reactor model which we have got is of order 5. It has one input, it has two outputs, and besides that it is nonlinear. Now just to, after having obtained the model, the job of the control engineer is to explore its time dependence, how it behaves in time for various representative transients. Okay, and there are control requirements. So in a nuclear reactor there is a demand, and for its operation in the linear range, the demand will be anywhere between 10% to 100% or 0.1 to 1 as a fraction of full power. And overshoot, generally we don't prefer in the operation of a nuclear reactor a overshoot. We change the demand at such a small rate, and we also design that overshoot doesn't occur. However, if at all it occurs, it should be well below 10%, otherwise reactor will trip. By trip means it is quickly shut down, noticing any danger. And rate of change of power is again kept small within this range, and reactivity addition rate is kept small by limiting the voltage signal to the control rod drive. And anytime the maximum positive reactivity or rod position with respect to the equilibrium is also limited to 0.001. So these are the usual control requirements. In any system one has to know the control requirements. For nuclear reactor they are something like this. Now we first look at the eigenvalue of the system, that differential equations at equilibrium, that equilibrium is H equal to 0. It has one large eigenvalue, this also large, this is close to the origin but negative, and two eigenvalues at the origin. If we see the control rod position inside the core, this is inside, shown negative. One of the eigenvalues from this 0 becomes stable, and if we see the core, the control rod motion outside, one of the eigenvalues, rather both have become positive. One of the eigenvalues become positive, and this one always remains at 0. So this is the characteristic as regards the eigenvalue at equilibrium. This is the situation which I have shown in the box. Now we subject the system to understand how it behaves to a transient. The system is at the steady state at t equal to 0, and the input signal is changed in this manner. A small voltage is applied for 10 seconds, and then a reverse voltage is applied, and subsequently it becomes 0. It will be the profile will be shown in the graph. So because that voltage is applied, during this transient, let me just explain. I think that voltage profile is not shown. This is the time. So between 0 to 10 seconds, the voltage is 0.5 volts. At 10 seconds, it is brought to minus 0.5 volt. And then, so this is 10 seconds, this is 20 seconds. Subsequently, it is maintained 0. So it's a kind of a single pulse, positive pulse followed by a negative pulse to neutralize that, let me say, and subsequently it is kept 0. Now the reactor power multiplied by that sensitivity Kn, that will vary like this, and also the output of the amplifier, which is measuring the neutron density, will vary like this. Neutron density and reactor power are proportional quantities, so I'll end up calling reactor power in place of neutron density. You should also understand that both are synonymous quantities related through only a scaling factor. So the neutron density will change like this, also the voltage will change like this. So what happens is that you see in the first 10 seconds, because the control rod will be going out, actually there may be the control rod position signal here, yeah, that voltage was like this. So during this, the control rod is traveling out. Now here it reverses the direction, so it is traveling in, and because this area is equal to this area, the control rod traveled out and then it traveled inside by the same amount, and so at the end its position is equilibrium position. So as it is traveling out, it is introducing reactivity, and so the neutron density rises. As it is traveling in, reactivity is becoming not negative but reducing, so that gives rise to this profile, and subsequently the reactivity is 0. So reactivity is 0, so this becomes constant, neutron density becomes constant. This is the profile that comes. One can also see that rate signal, as the neutron density is rising, the rate is also rising. Then when the negative pulse is given, the neutron density is decreasing, and so rate is negative from here onwards, and subsequently it becomes 0 as the system approaches equilibrium. So this is how the nuclear reactor behaves in a transient. One has to see and understand the behavior in several representative transients. I suggest the learner to go through these 2 papers, one written by me along with my co-researchers, and one written by these authors, Park and Miley. So go through this for further knowledge enhancement. What we have done is we have presented the nonlinear model derived, and then we have seen how it behaves in one of the representative transients. One has to do several simulations to derive a full understanding of the system characteristics. Thank you very much. We will meet again in another lecture.